Yeah. Rishabh, anything you would like to say?
No, so sorry, I didn't realize my mic is on.
Okay, okay, so is the screen visible?
Yes, sir.
Okay, let us proceed. So till now, what we have seen, particularly three types of learning we have seen, supervised, unsupervised, and reinforcement to be, if we categorize it in this way, and to be more clear in pictorial form. So in supervised learning, we have all the examples, the training examples that are given to us are leveled. That means the data, it, so here is my training algorithm that I would like to make. So this is my fancy training algorithm that I would like to provide over this data. But I also have an expert alongside me, which will look the data. So this expert will take this data and then he provides me a level of the data. So I get Xi, along with that I also get Yi. And then depending on that, I provide a model. My training algorithm provides a model, and that's the framework for supervised learning. Let's call it SL, supervised learning framework. So all the data that I can have an access to also has a corresponding level along with the value of the attributes. Whereas in unsupervised learning, if you look at the same settings in unsupervised learning, it is nothing but you just get the raw data. There is no expert involved there. So you have a training algorithm again as it is, but you get the raw data, which is basically Xi, but you do not know the level. You get this kind of raw data. And finally, what you admit is that you provide a model which tries to cluster or classify similar oriented data, and particularly this technique we use to detect outlier, to form groups, and all that we have seen in the past. Reinforcement learning has a little bit different setup. There the data not only comes with a label, but it comes with a deferred level, so as to say, because the data that we sense, as we have already seen, that we sense the data from the environment, and our agent or the training algorithm that we wish to make there in reinforcement learning just senses the state of the environment, and also it can provide an action to the environment to change its state, and in between it sees some reward. So this is the state, this is my action, and I get some reward. So depending on that, I finally come up with a model to control the environment or to navigate through the environment. So this is unsupervised learning setup, and this is a reinforcement learning setup, as we know. But in real world, often we find that all the examples will not be leveled, right? I mean, we do not get an ample set of leveled examples. So if you see till now, all the methods that we have discussed in the era of big data, we assume that those should be leveled in case of supervised learning, because deep learning and all that, since we need to estimate many parameters, so we need a huge amount of level data, but in practice that may not be the case. So for example, if you look at all web documents, you need to classify whether the documents belong to a certain type. Let's say it's a faculty web page or a student web page. In computer vision, in medical imaging, you can easily understand the curation or the leveling is very costly, because you need to go to a doctor to say that this particular MRI scan, what is the deformity it has, or maybe some kind of a X-ray plate or something. You need to see that which bone has fractured, which ligament has fractured. So you need a very able curator to make the labels, which is often very costly. And therefore, you may have many such data points which are unlabeled, but very few of them are labeled. In computer vision, most of these cases occur. Often in computational biology, because it's a submolecule particle level things, even in chemistry, some of the things that we may not even reach for all the levels, or we cannot identify everything. We have something identified, and based on that, we need to infer something, but we have a huge set of data. Now, the question that we can pose now is that, is always all the labeled data are only important? Can the unlabeled data point help us in learning? This is primarily what we will be going to discuss today. One is semi-supervised learning. As you can see from the name, It is not fully supervised. It's a semi-supervised, meaning that there are few sample examples and there are many unlabeled data points, but you do not have their labels. And in other form, there is the same thing we will also learn, which is an active learning. I often call it as an interactive learning, because consider the medical imaging analysis cases, because there you need to choose, you have a provision to choose and give the expert what kind of level do you want uh, for him to give. Suppose you have a doctor in your hand, but he is very costly, his time is costly, he charges costly. Now you need to be very meticulous about selecting the examples that you need to be leveled in order to make a prediction model better. So that's why, I mean, in this setup, in semi-supervised and active learning, we have a huge amount of data. A portion of it comes to expert. So let's say the portion is that will be leveled is DL, and you want to build a a learning algorithm. I said training algorithm, the same as the learning algorithm, that would take some of the level this data, and also it has an access to a huge level of unleveled data, right? Now, does this setup helps to predict a model better than if we do not at all give this, just in case of supervised learning case? So that we need to see. So two things we will see in terms of visualizing it. We will see two things, that unrestricted amount of unlabeled data is given and a set of labeled data is given. And the other setting is that given the data, unrestricted amount of unlabeled data, I mean huge amount of unlabeled data is given, I will ask the expert. So what the active learning will do, I will ask the expert. That means I will choose which data I need to get the answer. The expert will provide me an answer. And then depending on the result, I will again ask the expert the next data that I need a level from, he will give a level. And after certain time of asking, I will stop and produce my model. So that's what we will cover today. So let me ask you a very simple question. Let us start with the semi-supervised learning, that you have a set of data. So the data set that is given to you, there are some level data and there are some unlabeled data. So this is the data set that is given to you. And obviously level data is of the form of x comma y. X is the attribute vector and y is the level, and unlabeled data is the form of x you do not know. So what is the common sense? Does this unlabeled data distribution helps? I mean, what do you feel? How can it help? I mean, the algorithm will come from the common sense. That's why I asked this question. How does the unlabeled data can help us in prediction?
From labeled data, we can interpolate a label of unlabeled data and then use it for training.
Excellent. One a good idea. Anyone else? Okay, since I think Suhas it is, right? Since Suhas give a good idea,
Yes,
let
sir.
us let us try with that idea. I hope to cover that idea as a third method. I will cover three methods, but let me start with it because since it came up from your curiosity. So to refine Suhas' idea is that why not see when we do an unsupervised learning, what we try to do, we try to make a cluster, right? And Suhas is trying to say we will interpolate unlabeled data points to find its somewhat, I would say, pseudo labels, and that may help us, right, Suhas? I mean, to refine your thought.
Yes, sir.
So therefore, you can see what Suhas is making is that suppose I have some points, let's say plus, and some points I have, let's say minus. Now I have a huge level of data. Maybe some data are with this, like this way. Some are with this way, very much clustered. There are data like this. There may be some data like this. There are data like this. Now what Suhas is saying, you can see the points here. If I try to just make a kind of a cluster of it, now it is not fully unsupervised, because in fully unsupervised setup, I do not know what this cluster level is. But since some of the proximity points falls into this cluster, which is given as the level, then Suhas' estimation is that we will interpolate these things as a positive level, right, Suhas? Similarly, let me use another color.
Yes,
We
sir.
will interpolate this set of things as a negative level and then try to cluster. maybe we'll cluster it this way. Very good. Now, let us try to dig down a little bit on this idea more. So what does interpolation to do with informal setup? So one thing we can do, suppose we have some points like A, B, C, D, E, F given as level. So this may act as a node in a graph. Why I start as a node? Because since we are trying to make clusters and all that, then we need to know the cohesion of the points with others, right? That's how we form it. I mean, in this k-means clustering and all, effectively, we try to find the cohesion with respect to all other points, right? In k-means clustering and everything that you have learned. So what essentially this methodology or the common sense will develop, we will try to form a graph out of it. That graph will indicate what is the cohesion among the set of points which have some positive points to be as the center, and we will just run a k-means clustering algo for the cohesion. Now, there may fall some points here and here which can also be cohesive here and here, unlabeled points. I will have an edge on that. The edge are nothing but the cohesiveness between these 2 points in terms of distance, inverse distance, cosine similarity, whatever you can find. So this way, I may find some strongly connected components in a graph. I mean, strongly connected, not in the colloquial graph theoretical sense, but I'm saying that a strongly related components in terms of the distance. Those we can interpolate as positive and negative, and then we may classify all these points on that. There will be anomalies, as we can see, because this may be a different kind of a negative level. Your boundary could have been this if this were negative, right? Your boundary could have been this if these points are negative. There may be certain anomalies, and there are theoretical works to prove that you will land up into a pack learnable bound for that. But this is one of the approaches people follow, and this approach is commonly known as graph similarity based method. For semi-supervised learning. And one of the prime examples where it is used, see, I mean, you can easily understand where it will be mostly used, that when you can find an example or a scenario where your unlabeled points may fall in a proximity of the label points. There, this method is very much applicable. If your data is scattered, this method has a fallacy. As you can see, for scattered data, there may be cases where no points could be interpolated or near from any positive points, or maybe misinterpolated with respect to positive points. So there, I mean, otherwise, if the data distribution is scattered very closely with your given level point, then it is, so it is primarily one of the situation where it is used is when we have a CCTV monitoring in a store, or rather the common name is not CCTV, it's called webcam monitoring. What happens, suppose it is in a desk where a person, every day the same person takes the money and gives the goods, and there is, if somebody is making any fraud, therefore there is a CCTV camera. Now you can see all the points are very much clustered, because there is 1-2 points people have labeled that this person is a person who is from the shop, and this person is not a person who is coming to the shop only to purchase. So 1-2 examples we just have make such an estimation. Now see, there could be a lot of data, but since the camera position is fixed, therefore the distribution of the points with respect to the shopkeeper and the other points is very less distant, because all the other image inputs are same. Only the person who is giving money and taking the goods is changing. So therefore the proximity is very much. Now the negative example could be, there could be multiple people, there could be deviations in that, taking away some of the goods, running quickly. Now you can see that the deviations will be far apart from this. So this is one of the positions where we use this graph theoretic or similarity based approaches. And there, what we try to do, we try to minimize the distances, or rather the distractions between the edge similarities, and try to cluster accordingly. Okay, questions? This is a very naive method. That's why I started off with this. Okay, if not questions, can you think of something else? Suppose we are
Sir,
only
if we
leveling.
have
So,
a
Yeah, I mean one by one. Sir, if we have a level, then
if we have a distribution with unknown parameters, then we can
Mhm.
run the expectation maximization algorithm to estimate the unknown parameters.
Yeah, but the only problem here, you see, there is a expectation minimization algorithm is not an optimal algorithm. Number one, there you sacrifice. The second thing, your data points distributions couldn't be that good. That, see, already we are sacrificing because it's not an optimal, and if your data points is not that good, then you will end up with a very bad local minimum. I hope you can understand the fact, because you are iteratively closing it, right?
Okay, sir.
Okay. I guess some of the works are there with the expectation minimization, but I need to look for it. But it's not very popular in this sense because of this fact. Okay, let me give you a hint. Can SVM help for 2-class classification?
so,
Suppose the data is linearly separable. Yes.
so suppose we have 1,000 points, out of which 200 are labeled
Okay.
and 800 are unlabeled. So
Okay.
we can train SVM or decision tree classifier using these 200 points and
Okay.
then predict the values of 50 points. Let's say I am dividing the unlabeled data in
Hmm.
batches of 50.
Okay.
Every time 50 points are predicted, I will merge them with my labeled data set, and then with 250 points, I will again train my model. And I will keep on doing this until I have got labels for all of my 1,000 data points.
It is good, but the only problem you will have. Suppose I have this kind of levels. Okay. Now suddenly you got a point here as plus, you got a point here as plus, you got a point here as minus, you got a point here as minus. What you will do? Do you see your approach has some problem?
So I will try to ensure that those 200 initial 200 labeled points contain uniform distribution from all the data.
No, no, this is the distribution is uniform. See, uniform, I see, first of all, we are assuming IID distribution, that's for sure. But even if the distribution is IID format, that distribution could be like this. So IID doesn't mean that your distribution should fall inside a single circle or a single zone. This is also IID distribution with certain variance. I mean, you may say the mean and the variance. Depending on the mean and the variance, this distribution came up, right? Okay, just let me. This is a little bit tricky. I mean, this is one of the pioneer papers in ICML, the International Conference on Machine Learning, which is given as the test time award, because this particular idea has been used a lot even nowadays. So what they do, let's say we have this kind of level points. So what does your SVM will do? Your SVM will just try to separate with the highest margin, right? Now, if the data is linearly separable, obviously we assume that the data is linearly separable. Otherwise, we will use a transformation to make it into a domain where it is linearly separable. Now, along with that, suppose I have some unlabeled point distributions. And suppose since we are separating it with a line linearly separable, we assume that the margin is, we have a belief that there will be a sufficient margin. Now you see, depending on the distribution of the data, can't you think that your line this way I also could have been made, it could have been made and it is better, right? Yes or no?
Yes, sir.
So now you see that I will use the SVM, but with a twist where there also I need to take care of the margins possible by the unlabeled data, provided this optimization problem I will frame in such a way that the unlabeled data can take any label. Given the unlabeled data can take any label, can you maximize the margin? The SVM question will be like that now. Given the labeled data, your margin will be based on the labeled data and the support vector from the labeled data, that's for sure. But given the unlabeled points, if you assume any label, can it maximizes the margin? So let me make it formally write it. So what we are maximizing, what we are minimizing in SVM, we are minimizing argmin with respect to W. I hope you remember this, half WWT, right? This we are doing in SVM such that this YI, WI, or rather YIW, I mean xi is a point with multiple things, dot xi greater than equal to 1 for all I which belongs to the set of labeled examples. Right? This was the traditional SVM separation optimization equation, right? That we started off with only for the white points. Now see, what we will add into this is number one, that suppose for all points U which are from the unlabeled set, what I will do, that suppose you got a label like this, then with respect to all U, this should also happen. And I assumed a level of U. Now this level could be anything. So I will assume this could be belonging to either +1 or -1 for all U belongs to D. Now with these three, so suppose this was the original one, this one, and additionally these two constraints, if I could minimize this one, then obviously my margin will be this with these two constraints, not this one. Right? Yes or no?
Yes, sir.
Yes, sir.
Let me repeat it. See, what does this format is trying to do? This format is trying to find a margin, right? Earlier we found this as a margin if we consider only this one. Now the fact is that, let me just remove these two lines. Now the fact is that I have an unlabeled distribution as well. So that distribution, suppose I think this as positive, this as negative, I can think this as negative, this as positive, any possible label they can take. My only criteria is this particular constraint will keep this line within the plus and minus in between somewhere. Now these two constraints will enable me to find a boundary which will just make this margin the highest, because any possible valuations you can take, I want to maximize the margin. Maximization is due to this argument. So this approach is known as transductive SVM, and it has been proposed by Joachim in 1990. Okay, so this is one of the best papers. I mean, one of the machine learning papers people usually tell that we need to learn when we learn machine learning. One of the papers it's a must-read paper. So now the other thing is that we already know how to transform it using slacks and all. So here the only transformation we will try to make using slacks is argmin W. I'm trying to minimize half WWT. When I introduce slack here, the slack will be introduced with respect to labeled points and unlabeled points separately. So what I will do, earlier I only introduced slack with respect to labeled points. Now all the label points. Now I also introduce slack with all respect to all the unlabeled points as well. Okay, so I just call it this way, because why I give a cap, because this slack is dependent on which value or which level the unlevel point is predicted for that optimization. That's why this is a actual slack, because I know the level of it. This is a slack considering some levels, and that some level, again, you can think that such that the format earlier was for the original points or all the level points. Let me call it L greater than equal to 1 minus L, and my two new conditions which were I proposed for the unlevel points. So this is a predicted level of that must be greater than equal to predicted slack. And the second criteria was my unlevel point prediction can be anything, this or this. So this is for all level points belong to the leveled set. This is for all unlevel points belonging to this set, for all unlevel points belonging to this set. So this is the same thing, but with slack. Now, we are only discussing about the possibilities of formulating this into an SVM problem, but Joachim's paper has many things that he had proven that this approach will converge, frame optimal solutions or near optimals and all that. But the primary thing here is to note that with the introduction of these variables and due to this non-deterministic factor that we introduce in each of the cases, the problem now that we are tackling is NP hard. Why I bring out this issue? Because earlier, when we do not have this non-determinism into it, we can solve it. Remember, we can solve it using quadratic programming, right? Quadratic programming is a programming technique we can solve. I mean, it's a technique, mathematical technique. We can solve such constraint optimization problems perfectly. Now, since it's an NP hard, so in polynomial time, you will not get a solution. You need all possible combinations to explore to get the optimal solution, which inherently makes the problem non-deterministically polynomial time algorithm cannot, deterministic polynomial time algorithm cannot solve it. So therefore, what people used to do, they use what Joachim proposed heuristics to guide through this choice of non-deterministic values for YU. And particularly, he used a branch and bound method to prune and all that. And this branch and bound is very well established in AI. You have solved the n-queens problem. That's a branch and bound approach we use. We look for placing the queens in a chessboard. Then upon getting a dead end, we just retract back the previous and try to find alternative branches. So this kind of way, he tries to go with one particular assignment of WU in branch and bound. And with respect to heuristic, then he just comes back and flips some of the assignments and then go. So this is the method that is proposed in Joachim's paper. Okay, any questions? Okay, so now this, why I drawn this particular figure is the fact that in such pathological cases, this method has a demerit because we assume, so this method has an inherent assumption that the margin separability, right? We assume that our data is linearly separable and we have a decent enough margin to establish this large margin assumption. Sometimes we call it as a large margin assumption. So then what, this has a problem because, first of all, there could be many such possibilities by which we can cluster it, and think of the factor that suppose some point is noise. Then this method is totally haywire, because if some point that is leveled is a noise, then what to do? There are many follow-up papers after Joachim's work, some of them by the Tom Mitchell himself, where we found a difficulty that which of the boundaries will be the best, because these two are plus, these two are minus, so there could be many possible boundaries. Even you can draw a boundary like this, even you can, depending on the distribution of the points. So this boundary is also correct, this boundary is also correct, which of them we will take. So then there are some other papers and also the other methods to follow. But this is one of the best methods that people use and get successful sometimes in news group, reading a news article, categorizing what kind of article it is. It's a sports article or it's a political article. Such things people usually use this SVM because there the articles and the characteristics of the words form a very strong or a large margin in between. So it's a very widely used approach to categorize the news articles. Any questions? So we call it as transductive SVM, this technique. Okay. The second thing I will just smallly illustrate because this is also a very nice paper which we call as co-training. The concept is pretty nice. So this is by, I think, Blum and Mitchell. This paper is Blum and Mitchell sometime in 98. It occurs in 98. So this co-training says that suppose you want to classify a web page, whether the web page is of a faculty or that web page is of a student. Let us take this simple problem that I want to classify a web page, whether the web page is of a faculty or the web page is of a student. Now, what I will do, I will try to find out certain attributes from the web page. So to make things simpler, let us try to find out two features from it. Let's say X1 and X2 are the two features. X1 says, I will just look for what are the links that features inside a web page. So suppose this looks for the links inside the web page. And why does it matter to segregate the web page for a faculty and a student? Because there would be inside the web page, there will be links to its students, to its collaborators, which may indicate mostly that is a faculty web page. However, for a student web page, the links could be my advisor. Such kind of a link could be there. So that may classify it as a student web page. The second thing that we also take as an attribute that some of the critical text description we will also try to capture. How does it matter? Suppose there is a description inside the web page that I am teaching. I am teaching CS60050. So this means that if you could find out such kind of a phrase inside the text description of the web page, obviously this should be some faculty web page. However, for a student, that course is taken, such kind of a text description, obviously categorize that page as a student web page. Now, what we will do in co-training, I mean, what does Blum and Mitchell has done in co-training, that depending on this attribute X1 and X2, I will try to learn weak learners C1 and C2. So what I will do that, I mean, I can easily learn a weak learner depending upon the restricted attribute set or by a partitioned attribute set, I can learn it. They assume that this weak learner, if they classify based on this attribute some of the web page as faculty or student, and this weak learner classify some web page as faculty or student, the inherent assumption of this work is that these two are the same with respect to the optimal classification with the overall X attributes. But since we learned a weak learner, now how can we produce a strong learner from the weak learner? We know some of the methods, right? Ensembling will come up. But how do we ensemble here? What they did is that, see, after we have a C1 as a weak learner, weak predictor for certain kind of a web page as faculty or student. So let's say C1 will predict, suppose I have 3 pages, P1, P2, P3, P4, let's say 4 pages. C1 predict P1 as student, P2 as faculty. C2 predicts P2 as faculty, P4 as also faculty. Now, since these predictors are not very well in the overall, but they are good at any certain position, that's what the weak learning does. This level I will use again to retrain my C2. This level I will use again to retrain my C1 iteratively. This is the co-training part. So now you can see the beauty of it. See, I do not know, I only know some of the data sets, not all of them are level. I took some unlabeled points. Depending on the unlabeled points, depending on certain attributes, some of the weak learner can classify a cluster of those points well, not everyone. Other weak learners can classify the other cluster well. But since they have a confidence on what they classify, I will throw those data labeled intermediately to the other classifier and vice versa. In this way, we iteratively move on until and unless we do not increase the performance or the number of levels, we still go to that point. So this particular method is known as iterative code training, and this is also has been shown that web document classification, this is very much useful to classify web documents. Okay, any questions? Okay, so in summary, for the supervised, semi-supervised learning, we learned three approaches. One is graph similarity based, which you told me how to do it. We learned transductive SVM. This is very much useful in many setups because SVM has a very popular, SVM is a very popular choice because though your space to classify is very much non-linear, you can transform it, have a linear classifier. Even if the VC dimension is very high, but since you are supporting it with only a very small subset of vectors, drastically the complexity of deriving that reduces. That's why people most of the time SVM is a very standard approach to go for the classification problems. And also we have learned something called code training, which is an iterative approach and which sometimes uses two weak classifiers to learn the labels and throw each other to rigorously do it and make a consensus out of it. So the code training is basically for consensus of whatever we do over the full data set. Okay, so this is all for the is what I would like to say for the semi-supervised learning thing. Now coming, so I hope there are no more questions right here. Okay, now coming to the second aspect of it, which I will very briefly discuss, which is called an active learning. It is very much useful to a scenario because some of the time three things may happen. Suppose you are doing something on a, let's say on a circuit domain, where the simulation in low level circuits, it's a SPICE simulations in analog circuits are very costly in terms of time. So then you need to be very meticulous. Suppose you are trying to learn certain behavior of a circuit or some waveform, you need to be very meticulous about which example I should choose and simulate so that the outcome will give me the best result in terms of classification or some learning. So this is very important for the medical cases as well, as I already pointed that which of the thing that I will ask from a doctor to level that will help me out. So again, to give you a very naive example to start with, that how this helps, consider that you have a timeline. I mean, not it's a number line. Now there are certain points which I have as an example in the number line. Now, in terms of the truth value, let's say here, everything on this side is positive, everything in that side is negative. But you do not have this particular junction beforehand. You do not have this beforehand. What you have this set of points. Now, can you tell me by very basic intuition that which of the points you will ask for the labels? To understand where is the partition.
Sir, in the middle.
Suppose in the middle gives you negative, then what will happen? Okay, I probe it, I got a minus. Then
So then we can check
So
at a
starting
far away point.
this point, this is a plus. Then
So then
Yes.
it will be somewhere between them.
exactly. So what you are using? Do you the method, algorithmic method?
binary search types.
Yes, exactly. So you know you are 20 years late. All these otherwise have been a nice, I mean, seminal papers. But anyway, there is a theory behind it. You need to prove that this does and all these bad things and all. But the common sense prevails. I mean, you are great in that. So what we do is that I will ask for points in order to squeeze the boundaries of it. So as your friend suggested, I will ask for this middle point first, getting a negative. I will ask for a further point, either this one or this one. I mean, in a pathological scenario, you may first ask this one and get a different notion that this one might not help. Everything will be here is minus. So you ask for this and then converge it. Then you ask for this and then you ask for this and finally that. So suppose then you have n points unlabeled. So how many training iterations do you need, or how many asking to the expert do you need?
Log n to the base.
Yes, and exactly. So this is, you can see, this is an exponential improvement, right? Because log n with respect to n is an exponential improvement. I do not need n points anymore. I need just log n points to do that. And I mean, what the additional thing this paper has done, I think this is by Sanjay Dasgupta in 1999. I think Sanjay Dasgupta's work that you just predicted. 99. So most likely 99. I have to check the year. So Sanjay Dasgupta's work, he says that, I mean, what he proves is that to make the error bound, if your error bound is this much, what it proves, you need to make this many number of queries to complete the search. And which eventually turns out what you have found out, which eventually turns out with respect to the number, it is log n, because you know the relation between n epsilon and your confidence from the pack, right? It comes with ln root over, right? Remember? Ln root over 2m by delta, right? Epsilon is greater than equal to, this thing comes now. Yes or no? For what? I think 1 by 4. I also
Yes,
forgot.
sir.
I have to derive. So due to this thing, so I'm erasing it since it's not a correct formula. I have to derive. So using this thing, what happens is that it is basically log n. But this is a very simple example. And let us make it a little bit complicated. And again, try to invoke the SVM, as the SVM is one of the de facto standards everywhere. So for the SVM, what would have you done? Let's say we have 4 points like this, and we have 4 5 points like this. In case of SVM, how would I have done? There are many other samples. I mean, which sample do you have preferred? Let me draw the samples first. Suppose there are samples like there are also some samples. So in SVM, what would you have done? So with only the level points, this comes as something like this, with only the level points. Which example next you have preferred? Okay, 3 things we can do. Let me give the name, then automatically the intuition will struck to you. We can sample density based. We can sample uncertainty based. Or we can sample ensembling ways. The name itself is a hint. So which is the next point you would like to sample if we use density based sampling? What does this density should mean?
If the density at a particular region is high, then it is highly probable that all of them will belong to the same class.
Exactly. So I will try to find out a point whose density is higher, but which point among, let's say I found that this cluster is mostly dense. There are many more points here. So which one I will pick up? Farther one or the nearer one?
Nearer one.
Exactly, nearer one, because see this particular line is dictated by a margin. So if I pick up this nearer point here, this may be due to the fact that this point is unknown to me, so this line is little bit shifted here. So due to this, maybe the case that I have to shift the line a little. Good, this is density based. All these things, since you can take the intuition now you can easily frame that what I call optimization formula, because here you will assume a point whose level is plus or minus, which can maximize the margin, but close in the higher in the density there will be a constant, and close is a constant. What will be the uncertainty based? Where is the uncertainty here in this diagram with respect to the sparsity of the points? See, these parts are very uncertain, right? These points, maybe if I have something like this, these points, right? The points essentially that falls inside a margin are basically uncertain point, because those points may actually dictate your boundary to shift like this, right? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So therefore, those are the points you also can choose, which we call as an uncertainty-based sampling. That you next ask for the levels of those examples which is close to this line, but scattered away from your given levels. And ensembling is obviously, you can understand, it is density plus uncertainty. Both I will take into consideration with a weight factor to ensemble. I will take some W1 into dense point and W2 into this point, whichever is the max. I will take that point as the next. I will ask that point as the next to level. Okay. So this has been proven that, I mean, what that paper does, I mean, this is obviously of Sanjay Dasgupta's work in 2004 that I remember. This is one of the seminal paper. So what does this paper proves additionally is that this is better than the random sampling. And also this way eventually converges with, I mean, they have also have to give a proof that what fragment of points usually you do when you go for semi-supervised learning versus the active learning. Are you saving in your level, asking the levels, are you saving any number of points or not? So this is what is known as, so this method that we just described is known as active SVM. So we got three types of SVM thing, right? I mean, the basic SVM with Slack. Then we have transductive SVM for the semi-supervised learning. Then we have active SVM for this active learning. Just to finish off today's lecture, there is a very subtle difference between online learning and active learning. We'll also come across a paradigm which is called an online learning. In online learning, the only difference is that there is no provision of the training algorithm to judge which example you need next. In online algorithm, you are only given a selection that whether you need this example, just this is given and this is not given, you sample from what is given, how many points you need. So there is a set which is given level, there is a set which is where level is not given. In online learning, gradually you sample from which level points you want, which unlevel points you want. But you do not have the choice to ask, as opposed to active learning, you do not have the choice to ask for which point next I need. Okay, that's the difference. And due to that, online learning has also has a different ramifications and different algorithms. Any questions?
Sir, can you please explain how the SPICE simulation circuit is related to
Oh,
active
SPICE
learning?
simulation. Yeah, see, sometimes we want to know that certain waveform behavior, suppose you want to learn depending upon the waveform behaviors and the interrelationship between that, you want to learn what
Yes.
is the maximum value that function or that particular line is taking, what is the minimum value
Yes.
that line is taking. But to get the maximum value during simulation that line is taking, suppose a voltage line, to get the maximum and the minimum value, you need to have all possible ways of simulating, all possible parameter you have to set and do that. Now in Spice, one round of simulation takes days, even months sometimes, depending on the size of the circuit.
Yes, sir. Yes, sir.
So therefore, you need to set the parameters in a very accurate way so that you can get this deviations in a much larger extent. So there, you looking at one shot, I mean, looking at the one outcome, you just select what parameter values I will choose next and give my designer to simulate. Because once I give it, he will tell me I will take 1 week to give you the answer. Now in this
Yes, sir.
way, you need to have very punctual on the points. And later you will also find there is something called Bayesian optimization, which also is a type of active learning, but in a probabilistic sense, where we try to first we try to fit a curve by finding a point, looking at the activation of that point with respect to the other points in the curve, and try to squeeze it and find the curve. So there is another, you can just look into it, Bayesian optimization, we call it.
Okay, sir.
It is also used in the SPICE simulation cases.
Okay, sir. Okay, sir. Thank you, sir.
Ayan, I mean, the point you raised for the expected minimization has a little bit similarity on the Bayesian optimization. I hope Ayan raised it, right? From the voice, I can.
Yes, sir.
Yeah, you can see, you see Bayesian optimization, you will find it. It is not Bayesian learning, it's Bayesian optimization.
Okay, sir.
There we do this probabilistic methods. Okay, so that's all for today. Any questions? Then I can answer. Okay, so the final class will be on 14th as per our schedule. So we will just finish it up with a little bit on the explainability, that is the recent trend in machine learning research. I would like to introduce you that in the next class, because all the things we will see, explainability, fairness, biasness, and all these things are the recent trend. You should know because to contribute in this community. A little bit I will do that, and I will summarize what I have done in the next last class. So thank you. That's all today. Yeah.
Yes, sir.
Suppose
Sir, one
any
more question is
yeah.
this. Sir, for in case of SPICE, maximum time when we change the parameter, some of maximum the case is that some fault is there or some short circuit has been there introduced and some change of the result has been come. But for by using this type of thing, can it assure that the final result will be also
No.
same like this?
No, you do not mix with fault. See, I am talking about a general circuit without any fault. I want to
Okay.
say, suppose what this voltage value is taking, maximum and minimum what value. Now, if I want to predict that, you cannot predict it very easily, because then you need all possible parametric variations and need to simulate it. That is costly in terms of time
Yes, sir.
and tape out duration. So therefore, what we need to have some prediction going either through some of the active learning way or Bayesian optimization, whatever we use. There we will give you the parameters for a designer to simulate and give me the answer, and based upon that I will guess. So my guess will be more apt if I could choose appropriate parametric points. That's what the
Yes,
case.
sir.
Not for the short circuit and other case. There are other techniques to take care of this.
Okay, sir. Okay, sir.
And why we
Okay, sir.
need such thing? Because see, suppose you have designed a circuit and that
Mm.
could be deployed inside some of the other chips.
Yes,
There,
sir.
a particular voltage line should be, let's say, the other chip where it will be deployed has a restriction that this voltage line should not go above 2.2 and should not go below 1.4 volt.
Yes.
Now the question is that if you are standalone doing it and checking that circuit and that voltage line, now if it goes sometimes, then there is a chance of doing some damage, maybe burnout and something in the other
Yes,
side.
sir.
So
Yes,
you
sir.
need to test it, but you cannot test it fully because of the parametric variations. So somewhere you need to learn, guess, and produce. So sometimes we do Monte Carlo simulations. We call it
Yes,
Monte
sir.
Carlo simulations.
Okay, sir. Thank you, sir. I got it.
Okay, that's all for today. Thank you.
Thank you, sir.
Bye.
Thank you, sir.
sir.